You know, you have a story that existed and is long gone, and then science has methods to bring back, maybe not the whole original story, but some understanding. This is the list of science projects at Georgia Tech. I'm showing this slide basically because I promised I would. This is the list of scientific projects known by the International Office of Georgia Tech to be taking place in connection with Africa. I can tell you it's actually got many inaccuracies. But it does say a number of things. First, there are some of these projects, I called them scientific, I should have said research projects. Some of them are coming out of Ivan Allen, some very interesting ones. And the others have various sides to them. But I do want to make a point that a great preponderance of them, and this does connect with today's sessions, this morning's sessions, a great preponderance of them have to do with environmental issues and with health issues in Africa. And I'm going to make a couple of remarks connecting, well, telling mathematical stories that do relate at least to environmental issues, which in some way will make a transition, but we shall see. So there is a lot of science that connects Georgia Tech with Africa, and I hope we will be enhancing that. Now, mathematics is in some ways considered the most arcane of the sciences, but I want to try to make it a little more inviting by telling you that you should think of mathematics as an observational device. Just like a microscope or a telescope or a mass spectrometer. And in fact, we did see that also today because most of you found a little bit of statistics were presented and you found that palatable. The statistics allow you to understand. They are a way of organizing data and putting it in a form that your mind can take it in. So this is an example of an observational device. This is Hubble. Anybody looking at Hubble sees that this is quite a complex device, but you don't have to understand all of the complexities of how Hubble was put together in order to appreciate the things that Hubble allows us to see, which were never seen before. Okay? And so my analogy, my evangelism for mathematics is think of what mathematics can do as analogous to that. It's a kind of telescope or microscope. Okay, now one of the stories I have, scientific stories I have connecting with Africa, took place far from the Congo, the western tip of Africa. In 2005, I was in Africa to go to a scientific meeting. My other motivation was my daughter at that time was living in Africa, in Senegal. And there's a part of Senegal called the Langue de Barbarie, which is a peninsula. And this picture I took in 2005. In the background, you have the old French colonial capital of West Africa, Saint Louis, which is on an island in the Senegal River. And then the Senegal River, well, I have a picture of here's a classic map. I'm making a connection there with Ken's map exhibit at the Paper Science Museum. We have, by the way, if you haven't seen it yet, a phenomenal exhibit at the Paper Science Museum of maps with an African focus, and also of some things which are like maps, which I'll come back to at the end of my talk, possible. An old map of Senegambia, which shows the Langue de Barbarie. It's this tongue. It comes down, and the Senegal River flows parallel to the sea before it empties into the sea. You did at that time. Here, about the first of the two times I went to Senegal, this is a satellite picture of the Senegal River, which comes in from Mauritania and down the coast. It's mostly the boundary with Mauritania. And then an amazing thing happens. Here's Saint Louis, a little island, next to this tiny, or thin peninsula, a couple hundred meters wide and dozens of miles long. Okay, so just a very strange structure, and that tongue is the Langue de Barbarie. Now here's the kicker. Ask Google Maps what Saint Louis de Senegal looks like. And something is missing. Okay? And that something went missing in late 2003, shortly before I visited. I took that picture in 2005. And so there was an ecological disaster that was entirely man-made. There had been flooding at Saint Louis, and people had the bright idea of relieving the flooding by digging a 2-meter wide ditch across this sand spit. So this is an article by my friend, a mathematician at that time at the university I was visiting there, Marito Nyan. Marito Nyan is currently the higher education minister of Senegal, a very capable person, and part of the reason that there is a very good mathematical story I'm going to tell later about Senegal and the development of mathematics in sub-Saharan Africa. This is an aerial picture shortly after the ditch was dug, and you notice it's much wider than 2 meters, and you notice from the Google Maps it's now many, many miles. So back at that time, and now I'm get to embarrass my daughter, Marito was very concerned with this and gave my daughter and me and some other visitors, like Shuni Chow at Georgia Tech, if some of you know him, a tour of that breach there. That patch of water was land. And so the river shifted its mouth in a dramatic way. Now, what's that have to do with mathematics? Nobody's going to put the Senegal River or the Langue de Barbarie back together, even if this happened in an advanced country in Europe or North America. That's just hopeless. What you can hope to do is understand the effects of this and plan for them, and you can use mathematics in that regard. So the Langue de Barbarie created a very interesting commercial situation in Saint Louis because it had 2 fisheries. It had freshwater fisheries on the river, and it had saltwater fisheries adjacent across this very small, very narrow peninsula. With this shift in the river, Saint Louis became a tidal city. It was on brackish water, not fresh water. Really, the local economy was pretty much turned upside down. Now, what the applied mathematicians in Senegal immediately turned their minds to. So think of this as like Hubble. I don't expect you to understand, or maybe a few of you, partial derivatives. These are called partial differential equations. These are the microscopes by which we can understand things like how the tides are going to shift, how the brackish water is going to go up river, and to what extent and will affect the dams in the Senegal River, and the future flow. An imperfect understanding, but some understanding, which is obviously very important for coping with environmental problems, challenges. And there are similar modeling. There's similar modeling that goes on in mining-related environmental issues, but I haven't been involved in that. I was only marginally involved in this, but I want to show you that. So again, the mathematics brings a clarity to a problem which has important social consequences. That's my colleague Shuni there, and when we were visiting, and then these are some of the local applied mathematicians in Senegal. And there is quite an active mathematical culture now in sub-Saharan Africa, and I will say particularly in the former French-speaking parts of Africa because of the inheritance of the French educational tradition, which has the benefit, and sometimes people regard it as a curse, of being very math-heavy. But mathematics is a science which is not very costly, which has many societal, and I hope to convince you also, potential humanistic benefits, and you get a lot of bang for the buck for it. So it's a good story in Africa. So I will now, just to give you the tour of how mathematicians think, I will tell you the names of some of our tools, but gently, I won't go into the details. We actually, and distant African themes for the backgrounds here. So there are about 5 pieces of mathematics that we bring to bear on practical or even impractical problems. The first is modeling, and you'll hear applied mathematicians talk about modeling all the time. That's really a way of translating into the language that we understand. So that's generally the first step. Then we actually saw this morning some statistics. So statistics is the piece of mathematics which has been developed to understand correlations and averages and things. And as we know, political entities like statistics, even false statistics. But think of that as a lens that you've used which has some smudges and distortions in it. Yeah? It's still a lens. It could be improved. There's geometry, the study of shapes. I've illustrated that with, it seems to be blocked here, a work by a Makonde artist, which I think any mathematician that sees this will instantly be delighted by the geometric features of this abstract artwork by George Lemoine. We distinguish 2 different ways of understanding structures. One is geometry, which is the shapes, but then there is also the question of just what is connected to what, and we call that topology. And all of these subjects have been developed for centuries. They've got a lot of technique to them. I'm not going to go into those techniques, but I'm just telling you what they are about. And then finally there is analysis, and that corresponds in telling a story to putting all the details in place and finishing and polishing that story. It's the production. Okay. A very, very interesting and important trend in Africa right now is something called the Next Einstein Project. This was an idea that came about within the last 10 years. It was driven by some prominent mathematicians, some of whom were Fields medalists. Fields medals are the math equivalent of the Nobel Prize, more or less. Especially Neil Turok. So there were some people who were associated actually largely with the African Institute of Mathematical Sciences in South Africa, but also at the Perimeter Center in Canada. And they had the idea that we could make a real difference in Africa by growing an indigenous cadre of mathematicians in sub-Saharan Africa that could address problems with these tools that I've just described. The goal is to have about 12 functioning research centers, which will also produce master's degrees and probably eventually PhDs in sub-Saharan Africa. The mothership is the one in South Africa, but in 2012, an African Institute of Mathematical Sciences was opened near Dakar in Senegal. And the following year, one was opened in Ghana. I know the people involved in Senegal, so I'm going to mostly mention them. So this is a classroom in Africa. I think my daughter may have taken this picture. So as you can see, there's a structure that's been built. There are students, there are international visitors. There's quite a lot of participation in this by prominent mathematicians. Some of you who are Georgia Tech people may have known about the visit of Cedric Villani last spring. Cedric, a former Fields medalist who got his start as a Georgia Tech postdoc, has been involved in supporting this. You can see what they're doing. For instance, here, the workshop that, this is just from the website a couple days ago. The current workshop is Mathematical Tools for Understanding and Managing Fisheries. I wonder how Minister for Higher Education, Marito Nyan, got the idea of supporting that. But anyway, this is a very active, very positive story in Africa. So, I want to just say a few things about how a mathematical understanding could connect with African art and culture. And this is totally speculative, and I'm not feeling very in my comfort zone. I'm definitely out on that limb at Ken's behest there. So one way of organizing data is by just seeing what's connected to what. So I just gave an example from our exhibit to show a graphical network, and I'm going to pretend that what I show you now for the next several slides has to do with graphical networks. That's one way of organizing data. Now there's also quite a fascinating trend in the subject of, you may have heard of data mining. Taking vast amounts of data and understanding something about it. As you may or may not know, every year since the last decade, we have produced more data on this planet than in all previous history. This year, more than all previous history. Last year, more than all previous history before that. There are lots of data out there. And how do you understand data? How do you bring it to a level where a human being can detect useful features? Here's a really creative idea. Turn it into music. And I was quite skeptical about this when I first heard about it. In the last year in Atlanta, I've been to 3 events which understand data by turning it into music. And this makes a lot of sense at the fundamental mathematical level, because there is an ancient technique we have called the Fourier transform. It doesn't really matter how that works. What it means is any amount of data can be looked at in 2 different ways. It can be looked at in a spatial way, and it can be looked at in a frequency way. So in other words, you could look at the waveform of sound, or you could listen to it and you see different features. It turns out if you take complicated data and you synthesize it into music somehow, and you play it for people, your brain knows how to do this Fourier transform. If there is useful information in there, you will detect patterns intuitively and instantly with your brain after you hear it. So we had these 3 events in the last year. One of them was actually a concert. Actually, I think they've given this concert a couple of times, where they took evolutionary chemical data and turned it into playable music. We've also, at the recent Atlanta Science Festival, which I was somewhat implicated in, we played molecular music. We turned molecular chemistry into music. And just last week, there's a wonderful event in town. There's a Atlanta Science Tavern movement, and the European consulates partake in that. We went into the mathematics of music and the music of mathematics, and had some visual examples of how, if there are patterns, you turn something into music, you can hear them. I'll type things up pretty quickly. So I'm just going to now be really speculative and go to Ken's favorite subject. Ken has been wanting me to help him understand Lukasa boards, and you can see a Lukasa board at Paper Science exhibit that we have. What is a Lukasa board? So this is finally Congolese. I'm making the connections I can. It's a cultural artifact of the Luba people. It has information in it. We don't know precisely what information, because some of that's, I guess, lost to history, and in any case, it's sort of passed down in secret ceremonies and things. But what happens is there is obviously geometric information here on this board. And there's storytellers who take these boards and they read stories off of them with the aid of these boards. And those stories have history, they have personal relations, they have politics, political relations in them. We don't completely understand what that information is, but there are mathematical ways of quantifying how much information that is, and could be a help in decoding Lukasa boards. Actually, when I was thinking about what a Lukasa board must be, and mathematicians love to be self-referential, I thought, wow, what it is, it's a kind of PowerPoint. Because you see, I'm giving this talk right now. I could use the same PowerPoint slides tomorrow and I won't say the same words. I'll tell slightly different stories. But there are enough underpinnings in this visual that I can read, not read in a linear way of a narrative in fixed words, but that can be read in a multidimensional way. And tomorrow or a week from now, if I see these slides, I guarantee the words will be somewhat different, but there are underlying stories, multidimensional features that can be suggested by that. So I claim the Lucasa board is a kind of PowerPoint slide. It's a visual representation of stories rather than a linear narrative. So I'm just going to say a technique. I'm going to be a shill for 1 minute of my most recent mathematical result and really make a wild speculation about how it might pull information out of a structure. So this is this was a randomly generated network that I produced just to test a way I have in mind of connecting musical notes with information. And so this randomly generated network looks complex, but you can describe, there are different levels of complexity that you can quantify in terms of what mathematicians call a dimension. By dimension, I want you to think, how many questions must you ask to describe something? That something could still be terribly, terribly complicated, but if you're in 3 dimensions, you want to locate a point, you only need to ask how far right left, how far front back, how far up down. 3 questions. This network, as it happens, generated randomly, as measured by this wonderful formula, which is my latest formula in my paper accepted this month, relates some musical tones. That's what these things are. So think of this as Hubble. Don't get too turned off by the complex structure. Relates some musical tones to some other stuff, all of which is measurable except that number there. And that number there is a dimension. It says, how many questions do you need to ask to quantify this structure? And it turned out that the number in that complex network is 3. Maybe one can adapt these methods to a Lucasa board, do some statistical reduction of the data, put it in quantitative form, and get at least an understanding of how complex are the stories, how many different types of stories are they telling. Total speculation, take it or leave it. That's a mathematician's view on how we might, some new ways we might partner with the arts.